Okay, this is a differential equation, dz by d theta equals I times z, where I is a square root of -1. Z and theta are my variables. Z is the dependent variable and theta is the independent variable. Now, later on in the course you will meet solutions to differential equations, including ones like this, but I need to solve this differential equation in order to derive an identity which we're going to be using in complex numbers. So you have to bear with me. The method we're going to use to solve this differential equation is called separation of variables. And we're going to take the two variables, in this case z and theta, put one of the variables on one side of the equation and the other variable on the other side. So I'm going to divide both sides by z, so I get 1 over z. That will give me then dz by d theta, but I'm going to multiply both sides of the equation by d theta, and I end up with that. Now mathematically that operation, or this line, is not correct because this is not a fraction. This is referred to as a derivative. It's just a bit of notation. I know it looks like a fraction, but it's not. It's the rate of change of z with respect to theta. It is itself its own notation. So I can't really treat it like a fraction as I've done here. And this equation at the moment has no meaning. It makes no sense. But there is something that we can do to make this equation make sense. Something very simple. And you don't need to know the proof of it, but it always works. And that's just to pop in an integral sign into both sides of the equation. And suddenly it does make sense. I'm integrating now 1 over z with respect to z, and that's going to be equal to the integral of I with respect to theta. Okay, so two different integrals. And this equation is completely mathematically fine. There's nothing wrong with it. So now to carry out the integrals. So 1 over z integrated is the log of z, natural log. And that is equal to the integral of I with respect to theta. So I is just a constant, so it just becomes I theta. And then of course we have our arbitrary constant of integration. We're going to get rid of the log by raising both sides as a power of e, which I can write as e to the I theta e to the c by reversing one of the exponential laws. And then I can write that as a1 e to the I theta, where a1 is e to the c. Now c is an arbitrary constant, and e is just a constant, okay, Euler's number 2.71828 and so on. So this is just a constant as well, and because c is arbitrary, I can redefine my arbitrary constant as a1 in terms of c. Okay, so that's what I've done here. So a1 is now my arbitrary constant, not c, and that's fine. I've now found the function, which in this case is z equals a1 e to the I theta, and that satisfies that differential equation. Perfect, great, nothing wrong with that. But I know another function which satisfies that differential equation. Let's draw a line there. We'll come back to it in a minute. Let's take the function again. So dz by d theta is equal to iz. And the other equation which satisfies this differential equation is z equals a2 into cos of theta plus I times sine of theta. So let's differentiate that with respect to theta. We get a2 into minus sine theta plus I times cos theta. And if I take z and multiply it by I, that's going to give me a2 into I times cos of theta. Okay, times that by I. Times that by I get I squared, but that's just minus 1. So therefore, z equals a2 into cos theta plus I sine theta also satisfies this differential equation, because dz by d theta is equal to I times z, which is what this differential equation is. So because they are equal, this satisfies that differential equation as well. But there's something in maths which means that a differential equation must have a unique general solution. So these two functions, so this function and this function, must somehow be related because they are both solutions to the same differential equation. So with that in mind, we can state that AE to the I theta must somehow be identical to cos of theta plus I times sine of theta. Okay, where the arbitrary constants A2 and A1 I've combined together to give me a new arbitrary constant, A. Well, it's not arbitrary anymore, actually. So this must be true for some value of A. It must be true. So to find the value of A, what we're going to do is we're going to substitute in theta is 0. And this will give us A times e to the 0, which is 1, is identical to cos of 0, which is 1, plus I times sine of 0, which is 0. Therefore, we obtain that A equals the number 1. What does that tell us? Well, if we take that now and plug it back into the line above, we get that e to the I theta is identical to cos of theta plus I times sine of theta. The definition for exponential, complex exponentials. We can go one step further from there. If I take that now and I substitute in theta is pi, and I end up with a very special identity referred to as Euler's identity. So I get e to the I pi equals minus 1 plus 0. Okay, cos of pi is minus 1, sine of pi is 0. So that gives me then that e to the I pi plus 1 equals 0. And this is a very famous mathematical identity referred to as Euler's identity. And the reason why mathematicians like this one is because it's very simple and it summarises a lot of mathematical fundamentals within itself. So we've got three fundamental constants, so e, I and pi, are used a lot in mathematics. We have three fundamental operations, so we've got addition, multiplication and exponentiation, and we also have the additive identity and the multiplicative identity, all summed up in this one little identity. That should actually be like that. Well, I say it's always equal to, everything here is just a constant, they're just numbers, so actually equation, identity makes no difference here.